Hello. Now in this video we will discuss about one of the example programs that you saw during tutorial in week 2 that correspond to the program number 4 or number 5, I don't remember now, but I think number 4. So in which I asked you to play with the data, one of the data set, and do something with the LiDAR. So that program also telling you, explaining how to use the API, certain library, which is very useful for us to interact with the dataset for playing back the data, and also offer some helper functions for simplifying some part of the processing, and some also type of animation, so you don't need to do everything from scratch. Initially, you had this program which you could modify to add whatever you need to add for project number 1. Okay, so this is my program. So there is a function main, like in C. Okay, you put whatever name you want here. In fact, MATLAB doesn't like to have a different name for the main function and the name of the file. So you should use, if you want to avoid this warning from MATLAB, proper name. Good. So this is having some comment here. The first step that we need to perform is usually initializing the library, the API. This is the very first step. But maybe now the first that we have to do is to explain what is the program doing. So I will show you, I will run this program, and it's going to open a couple of... This is showing two figures. In one, I'm showing something that is happening in the global coordinate frame, because I want to show certain activity here. And also there is other, in which I'm showing what is going on in certain local coordinate frame. In this case, is focusing in data coming from the LiDAR number 1. It's a LiDAR which is pointing ahead the platform. And I'm showing information in polar, the native representation in that data, and I also convert it to Cartesian. And I also showing here all the points, the scan, which are normal surfaces, and some other points which are very highly reflective. So the LiDAR is detecting the intensity of the reflection. I'm showing those in red here with red crosses, because they are of interest for us. What is this coming from? Okay, the platform is here at this moment, at this position. There are, in this figure, you could see the certain infrastructure. These are walls, and these are certain landmarks, poles, whose surface is painted in some highly reflective material, so that they appear highly reflective. These correspond usually to poles, and the other, which are in blue here, correspond to these surfaces which are not very brilliant because they are normal surfaces. So, but I'm showing here in brown here, which are walls. They should be sort of blue here very usually. And the one that you see highly reflective, they usually correspond to poles. All right, I'm showing also in this global frame those walls, the landmarks, whose position we do know in global very well. So this is what I'm creating this. This is a static plot because we put this thing here and we don't need to modify at all during all the playback session. And I also plot in the ground truth, the path. More exactly, I know the trajectory in time and space of the platform because this corresponds to an experiment that was already done for which we had the ground truth. So we know now all the position and orientation the platform had during that trip. And I'm showing here the current position in this simulation, this playback session, of the position and orientation of the platform. I'm using this small rectangle here. And I put some controls here to allow, to do this. I'm moving this in a high-speed way. I could finish and I could reset this thing. So if I do reset, it's going to go to the initial point again. Each time that I do reset, it's going to repeat that thing. Okay. I'm going to finish this now. All right. And we continue talking about the program itself. We continue inspecting the program. So this is the initial part of the program. Initially, we do all this creating variables, creating figures. This is the initialization part of our program. And many things that we create here are going to be used later in a periodic way, in each iteration of the event loop. So first we do is initialize the library. This is what I'm doing here, and creating this object, which is an instance of the library. And this is going to offer a lot of methods of certain functions, which we could exploit. Also, we tell using one of the functions here, I have a certain function load data file. So we specify the file of the data set and it's going to load that thing. If that file is correct, if that file does exist and the format of that file is the proper one for a data set, this flag, because this function return a variable. So I put this name R here. If the flag OK say that it's higher than 0, so we know that it's OK. If that is the 0, a negative number, that is telling us that something was wrong. So there is no way to continue. Good. And it's also giving some extra information that we may use later. All right. So after that, I decide that doesn't need to be the order. I could do this before that, before loading the data set. I decide to create some local variables which are pointer to function, handles to function. And I ask in those pointer or handle to function from the API. I'm not executing this function, but just getting these fields, which are, if we think in terms of C, they are pointer to function. But they are handles which are representing which are pointing to certain function. So I put this using these variables, which are friendly name for me. Read next event, convert range to Cartesian, blah, blah, blah. We are going to see this later. Here we have all the explanation. And there are many other functions which are not useful in this example being discussed now. Okay, good. There's another API function which I'm calling directly from the API structure, which is providing certain useful information. That corresponds to how was the context of operation, the walls, the poles, and the initial condition of the system, and some other things which we may need for implementing our program. There is another function which gives you the full ground truth. It's a full trajectory in X, Y, and Phi during an old experiment being sampled at the LiDAR timestamps. Okay, we want to plot that. This is the one that I'm plotting in green. If you see the program that we had before, I'm going to run this again just to remember that thing. Here it is. Yes. I stop this. And this is the green one. This is the full. I'm plotting the position corresponding to that trajectory of the ground truth. Yeah. All right. We're going to see a bit more later. Put this here. Okay, and then we see this program that is doing that. I put this in this variable. This will be an array of 3 by whatever number of samples we have about the pose of the platform, the actual pose of the platform. Good. Put some comment here, and then I decide to create certain figures. One figure for showing, in this case, the global coordinate frame and certain infrastructure and certain animation here, and another one which is going to be for showing the the LiDAR number 1 scan, the scan from LiDAR number 1 in polar, showing the highly reflective points of that scan, and I also showing that thing in Cartesian. This is what I'm going to show here. Okay, good. I had to create those figures for doing the proper animation later. So I'm here, I decide to do this inside of this function, in which I specify, I want you to plot the ground truth that I know a priori, and I also want you to create that figure in figure number 20. So I go to that one, and you see that, yes, I expect certain FF, which is the figure number. I'm creating that figure here. I clear everything. And I extract the first 2 rows of this, because remember, this is 3 by n. I get the first and the second row, which correspond to X and Y component for all the samples. Yeah. And I decide to plot this in the figure. Okay. And I plot in green. That is why it appears green in the figure. And I want to tell the MATLAB, oh, I want to keep plotting things, so keep the other ones. I do hold on. And I plot this empty thing just to produce a handle, because I want to use this handle for dynamic plotting later. And I put some extra command for creating a grid and scaling to be, respecting the scale of X and Y equally. Okay. I specified this is the region I want to see initially, -5 to 20 meter, -5 to 20 meter, assuming I'm working in meter. Put some level, and that's it. All is done here. So this is the function that I call here. Here is, okay, number 20. And then I get these handles, which are, I put this name, HH in global coordinate frame. There could be one or many, because I could have many graphic objects here, which I want to update dynamically later. And in fact, in the project, you will include more. And I decided to add more things here. I could have added this thing inside of this function, but I decided to include this extra plot in this figure outside of this function. So I could ask, remember, I got some info. I put this in certain place. I forgot to mention a moment ago this thing. I had this API that give me about information about the context of operation, many things that I do know about the experiment. Okay, that's going to be in this, using this API function. You have to call this just once and get this structure with all the information that may be useful for us. And I decided to use this structure with information about the context. And I'm using this here for, I put context, it's a component of this structure, useful info, and there are certain walls and landmarks. This is what I'm plotting finally statically here. On the walls, for which I use brown color, and I use landmark, which I'm showing using these stars in magenta. And you remember I did plot the ground truth, at least the position here in green. So this is what we have here. And I also create this red star here for showing the position later dynamically of the platform. Yes. And this is what I did this here. And I also create here another object, which I'm saying initially is a 0, 0, that is doing nothing, and it's going to be red, and it's going to be continuous line. That is the one that I'm going to use later for showing this little triangle to show the current position and orientation of the platform. Yeah, this is what I do. And I put this using through this plot, which is showing nothing at the very beginning, and I'm generating this handle, so that graphical object could be updated later. Good. And I say, okay, there is nothing else to add in this figure, so I specify hold off. You may need to do this or not. That is not relevant now. Okay, and I decide to create another figure, which I decide is going to be figure number 21, which is the number 21, which is here, in which I'm going to create all this graphic, object here. And if you go inside this function, it's doing that. Yes, it's creating this figure. It's dividing this in subfigure number 1, number 2. I'm dividing this in 2 vertically, 1 horizontally. So this is why I'm using subplot 2 vertical, 1 horizontal, and they're going to be number 1 and number 2. Okay, this is what I'm saying now. I'm pointing to one of the 2 vertical, one of the only 1 horizontal, the number 1, which is this one. And later I create a second one here, which is the number 2. Okay, in the number 1, I'm going to create some object for the showing the ranges of the full scan, which is going to be covering from -75 to +75 degrees, having a resolution of half a degree. So they are going to have 301 ranges. And I'm showing here with the proper angle from -75 to +75, and I'm showing the ranges here. I did create this before. This is what is showing now, but when I do create that thing, which is here, make figure to plot LiDAR 1, okay, in this figure number, I specify something here for creating that object. And here I'm creating all the handles I need for refreshing these 3 things. The ranges of all the points, the ranges associated just with the highly reflective measurement of that scan. And I also showing here X and Y, or more exactly the point in Cartesian, yeah, all the point of the LiDAR scan. This is what it was. I did create in this figure here. You could do this in different way. You don't have the obligation to do the same style. You decide how to do that thing. This was just an example, because I want you to be, get used to do this kind of dynamic plotting, because things which we are trying to show, they are changing dynamically, and we want to see the evolution of those in our figures. Good. And everything is happening here. I think you could discuss this also with the demonstrator during the tutorial. They will explain you how to do these things. And of course, you could go to MATLAB and ask for help. Many people using this kind of thing for showing animation, basically, in addition to do the static plot that we usually do. Okay, good. that is creating that object or that figure having many graphical objects. And this is what we did here. Okay. And then I decide using this API function, okay, I create some controls here. This is the one creating this menu here, which allow you to continue playing, to reset, go to the very beginning, reset, go to the very beginning, to stop, to continue, and to finish. Okay, bye-bye, and it's going to finish. All right. Good. And then we see, okay, you did all this, created all these interfaces for interacting with the user. And I need to get them I'm creating two, the same controls are in both figures. You could have even more figures. You want to have the same control for them because both are going to do the same thing. Continue, they are synchronized. Yeah, you could do this or this. Okay, you could do the same thing. It's going to be okay. Yeah. All right, I'm going to stop this now and keep discussing about the program. So in the program, I keep initializing other variables because it is useful info that we got, from using the API just once. There is a lot of information. One was information about where are the walls, where are the landmarks in this context of operation, where was the initial position and orientation of the platform, and also is providing, you have LiDARs, okay, you had two LiDARs, what was the configuration of those LiDARs, so the position on the platform. So where was the position and what was the orientation of that LiDAR number one in the car coordinate frame. Yeah, we need to have this information because we need to do all this transformation from local in the LiDAR to global. So that means that we have to go from local LiDAR to local in the car coordinate frame to global in the global coordinate frame, doing the proper transformation in certain cases. Okay, so this information or this parameter could be obtained but by knowing how was the position and orientation of the LiDAR installation in the platform coordinate frame. Here it is. Okay, good. This is what I'm not using this in this program. This is why MATLAB is telling me, you are creating this variable, but you are not using those. Okay, yes, because in this example, I don't need to do that. Good. The same here for the initial pose. Useful info, pose 0, that is telling you that was at time 0, what was the initial position and orientation of the platform. Okay, good. I do create some other variables here. This is for storing the last value or the last measurement from the depth reckoning sensors, from the speed sensor and from the heading rate sensor, from the gyro. I put this. Initially, I don't know the value. I assume that they're equal to 0. But as soon there is a depth reckoning event, we're going to refresh these variables. And I also say that the initial time is 0. Okay, good. These are my program variables. And after that, after I did initialize everything, I may need to initialize some other things. That could be the case in your solving project 1, different part of the project. You will need to initialize some extra things because you may need to create other features in your program which are not here. Good, because this is just a basic example. Good. And then after that, we had the event loop. Yes, I put an infinite loop here. Keep looping here. It's going to end due to other event here. So in this case, each time that we do an iteration here, we use this function, read next event. Remember that was a local variable whose content I got from the API, and that was a pointer to certain function in the API, which the functionality of that function is give me the last or the next event, because we are, playing back chronologically all the sequence of events which were measurement for us, because these events, this measurement did happen in that experiment. So we are reproducing that following the same sequence, the same timing. So that is what's happening here. Give me the next event. In this case, it will be the first event because we are just running this for the first time here. And then we had to extract certain field because this is a small structure which contains the timestamp. It is using certain units. It's an integer number of 32-bit and sign in. And that is expressed in time in unit in which one count is 100 microseconds. So I convert into a real number, in this case to double. And I multiply by this constant because I want to convert this to seconds, because I expect to use time in seconds in a real number, not in an integer number. Good. And I also calculating here the delta time since the previous event. That may be useful in certain cases. At this moment, maybe we don't care much about that. All right. So we continue here because this structure, this E, I use this name because it's an event instance, and also has information about the type of event. Here it is. And that could tell us this is a dead reckoning event because they are measurement from the speed sensor and the gyroscope simultaneously, or because it's a LiDAR event which is coming with two measurements, one from LiDAR 1 and LiDAR number 2, which are synchronized, two scans, or there could be other events if we were using other sensors as well. Also, when we are interacting with the thing, we could ask, when we do reset, it's going to also send an event telling us that the user did press reset. So you know this in your program to take certain action if you want. But anyway, the important thing here that mostly the events are due to measurement. Yeah? And they are happening at different times. All right. So this is what we need to use to decide what to do. If the event corresponds to a dead reckoning event, we will do something. If the event corresponds to a LiDAR event, we will do something else. And also, some event is number 0, type 0, that is telling us, okay, that's it. The playback session did finish because we reached the end of the playback historical data. Okay, good. I have a switch here, case to dispatch. You could use if, whatever you want. I use switch here. Okay, and if event 0, I finish. I do break, that's it. I just stop this main loop. Yeah. If the event is type 1, oh, that is a LiDAR event. We need to do something with the data. And the data, I read the data here. I use this easy name, D of data equal to E.D. The .D here, because it's a LiDAR event, is going to contain a sort of metric 301 by 2. The first column corresponds to a scan from LiDAR number 1, and the second column corresponds to a scan from LiDAR number 2 because they are synchronized. And this will be an array of 301 elements, each of them. That is why we have 301 by 2 here. But individually, this will be a scan, 301 by 1. And they will be classed and signed in 16 bits. And in that, each element of those is going to give information about the range, the distance to the surface, which is reflected in that direction, and the intensity of the reflection. This is what's going to happen. And this, remember, we have 301 samples because they do correspond to 301 direction, from minus 75 to plus 75 degrees, having a resolution of half a degree. Okay. All right. Good. We got the data, and then I have this function which you are going to implement yourself. In this case, we are using the one that I got from the API, okay, in which I provide scan number 1, or more exactly, scan corresponding to LiDAR number 1. This is the column number 1 of this, remember. And this function is going to return the ranges in meters using single precision representation. And it's going to also report the intensity of the reflection, which is going to be an integer number, an array of integer number. It will be 301 by 1, single precision, and it's going to be 301 by 1, unsigned int 8 or 16 bit, I don't remember now. Okay, and this should be, if I put some variable here, the ranges in original representation, unsigned int 16 bit, and it's going to be talking in centimeters. But we don't use that thing, we are using the one in single precision, talking in meters. And I could do the same for the second scan, but I'm scan LiDAR number 2, but I'm not doing this now because I don't have interest in doing any processing with that one. And here I'm explaining something, blah, 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 blah. You could see that. And I want to ask certain other things to the API. Okay, I could ask, okay, what is the current pose, the actual pose of the platform at this time? Because the system or the data set is offering the ground truth. Tell me what is the current actual position and orientation of the platform. We have that advantage because this dataset does offer this to us for validating our processing later. Okay, I put this in pause GT now. That is the current pause of the platform. Good. And then I'm talking about the LiDAR again, and I want to convert this to Cartesian. And remember, these are the ranges, the 301 ranges, which correspond to 301 direction, from minus 75 to plus 75, every half a degree. I know implicitly that thing, and I don't need to show include that here. This function already knows that, and it's going to convert this, which was originally in polar, to Cartesian. That is why it's returning to a rate. And this is going to 301. This is going to also 301 by 1, and each of them will correspond to the component X of each of the pixels and component Y of each of the pixels. Yeah, you could do whatever you want later with that. Okay, good. I want to know more. I want to identify which pixels are highly reflective, or they do correspond to highly reflective surfaces. I could analyze the intensities because this is also an array 301 by 1. And if the values, certain values are higher than 0, that is telling me that in that direction the reflection was very intense. So I'm going to say that there are brilliant surfaces, or those pixels correspond to reflection from some surface which is highly reflective. We usually correspond to our poles, our landmarks, because they are poles which were painted, in a highly reflective paint. Good. I use this function find in MATLAB. You could investigate what it's doing. That is telling me the indexes in this array in which we satisfy this condition. I'm asking which element in this array do have a value higher than 0. And if there are 5, this is going to an array with 5 elements, each of them going to be the index in this array. And that is the finality of the objective of that operation here. Because later I want to show which are the pixels which appear to be highly reflective. Okay, good. And then I call this function, which is using the handle that I did create before, for showing the information in the local coordinate frame. Yeah, I have the handles here, and I specify the ranges and the indexes which correspond to the highly reflective pixels, and I also provide, X and Y component in Cartesian of the data. And this function is the one that is here. You analyze. Yes, it's having using the handles. What is the function? Here it is, yeah. And then I'm using the function set, because I use the 3 handles here. Remember, there were 3 handles. You remember, I have 3 handles for this guy. One for the ranges for all the points, some other handle for showing the highly reflective point, and some other handle for showing the position in X and Y. So they have 3 handles. And I'm using this properly here, for showing this animation. And this is happening at each of the LiDAR events, because I read the information from the LiDAR data. I do some processing here for extracting the ranges and the intensities, and I also do some calculation for obtaining the Cartesian equivalent and blah, blah, blah. And that is what I'm using here for showing these things. Okay, good. I also, if you remember, this was the handle number 1 in this one, array of handle. That was a red star, which I use for showing the position of the platform in the global coordinate frame. And I have the ground truth. Yes, and I know this is the red. Oh, no, this one, sorry. Okay, the red star here. That is the position of my car at this current time in the playback session. Good. Which is, of course, following the green path, because this is just one. That is the position of the platform at a particular time, and this is showing all of them in the trip. Okay, yes, that's okay. What is this triangle? What that is, if you remember, also the certain graphical object which I named H car. You remember that one? We did create this in certain place here. I think that was the one. I say, it's going to be red. Initially it's at 0, 0, and This red line is going to show nothing because it's just 1 point here. But later, I'm using this animation function, telling that function, I have this handle. We define certain thing in the graphical context. I want you to exploit that one to show shape in your library internally number 1, which is a triangle, of the position and orientation. And that is why this animation function is showing this guy. I keep moving that thing, and it's because I'm calling that function, specifying different pose. You keep, doing the animation of that thing. Yeah, that's all right. Good. That it was doing this thing, and I put a pause here so the system runs sort of slowly. Yeah, every time that there is a LiDAR event, I want to wait for 50 milliseconds because I want to see this animation happening. So you could change this value to make this faster or slower. You decide that thing. That is what I'm doing in this program if I want to show or do something with the LiDAR. I did that basic processing. Okay, I had to read the event, had to read the data, and I need to do some conversion of that data to whatever way is convenient for me. And after that, I could do some animation if I want to show some animation or not. And that was doing this program. There is other type of event, which is event number 2, which is that reckoning information that's coming from the speed and the angular rate sensor, or the heading rate sensor. But in this case, I'm reading the data, but I'm doing nothing. I put this in variable BW, longitudinal velocity and heading rate. This should be omega, but I don't have omega here in plain text. And I put this as a vector 2 by 1 because these are eventually the input of my kinematic model later when I implement the kinematic model. And I keep this anyway just in case. At the moment I'm doing nothing. Good. And there is another type of event. I say, I don't care because I am not expecting to process any other type of event. I would do nothing. So that is what happens when there is another type of event in this case. So we do nothing. And that is the end of the loop. And that's it. That is an API for printing some statistic that how we are using the API itself, but that is not relevant for us. And that is the full program. This is what is doing our program. So you may say, okay, what should I do now? Well, now we need to solve. Yes, we were asking you to do certain thing in that tutorial. For instance, I asked you, you should be in condition to convert whatever you see locally here. I want to see that thing globally. Are we in condition to do that? You say, yes, we should be, because this is the, I have information of the LiDAR points already in Cartesian in my local coordinate frame. Remember, this is X pointing ahead my car, and this is my left, and this is my right in my car. If I were driving this car, I would be facing here in the direction of plus X, and plus Y is my left, and minus Y will be my right. So I do a transformation of this, and I could convert all these dots, which we have here in the local, or in the LiDAR local coordinate frame in Cartesian. I could show this in global. How could I do that thing? Well, you could do that because you do know the position of the LiDAR in your car. What is that information? That information should be, I remember, in certain place. I put this in certain place. What is that? I think here it is. That is information about the LiDAR installation. Useful info, LiDAR's configuration, .LiDAR1, .LiDAR2. This is telling you X, Y, and Phi of the pose of the LiDAR in the car coordinate frame. How was that thing installed? And for sure this one would have that the Phi is going to be 0 because that one is pointing ahead, perfectly aligned with the truck, with the car. And this one is perfectly aligned, pointing back. So this will be 180 degrees or pi in radian. Yeah? And it will be certain also X and Y here. So we do know how to convert this in LiDAR coordinate frame to the car coordinate frame, and from the car coordinate frame we are in condition to jump to the global coordinate frame. How is that possible? Because in this case you do have, I indicate here again, you do know the current position of the car and the current orientation. Where is this coming from? I do know that in this case because I'm calling this function. Let me see what is that function. I forgot where I put that. It should be in some place here, in which here it is. get the current ground through. Pause. Yes, that is telling me at this very time, at this time of this event, I want to know the position and orientation of the platform. And we have this here. So, if we know the position and orientation of the platform, and because we know the position and orientation of the LiDAR respect to the platform in the platform coordinate frame, so we are in condition to know the position and orientation of the LiDAR in the global coordinate frame. It's just transformation. Good. That allows us to do the conversion for from the local coordinate frame of the LiDAR, whatever point we detect there, we are in condition to convert this to global. So we are, and you are in condition to show this in here. And you will see that if you are doing things properly, you will see that all these points are going to be hitting these walls. Yes, because this is what we are detecting here. I continue with more. Here is. Now we are in range and we are detecting. In this case, we are parallel to the x-axis, fortunately, because the car has a trajectory here was almost horizontal in this plot. So, and we are detecting certain dots here. Yes. This is due to the discretization of the LiDAR, because remember the integer number in centimeters, and they are about fraction of centimeter. So that is the quantization error. So we are scanning this thing, and it's going to appear here. So you see here, in this case, we could do this mentally, because we see that the car is here, it has a field of view plus minus 75 degrees, it's detecting this thing and this thing and this thing. This is why you see all these dots here to correspond to here. All these dots here will correspond to here. And all these dots will correspond to the poles. You will see they are detecting at least a couple of reflections here will correspond to these poles. And there is also some occlusion because the LiDAR is scanning here and this object is occluding, so there are some holes here. It's not in this certain point here because they are in the direction here, which is being occluded by this object. All right. If you were in condition to convert this to global, and you were showing this dot here, they would appear here. And you will do that because that is the validation to verify that your transformation are being calculated properly. Good, this is what is happening now. So, what are going to be in our program? Well, you will need to do all the calculation here for converting whatever you saw locally. You are detecting here locally from the LiDAR scan. You will do the proper transformation from local LiDAR coordinate frame to global. And you may have some extra object, graphic object. You may have created, when you created, suppose the first figure. When I did create the first figure, in which I create also many other things, I put also the walls and everything. You could have created as well, if you wanted, some graphical object for showing dots or points in that coordinate frame as well. And those would be the point that you would calculate, converting from local to global the LiDAR scan. So that is something that you will do later. Okay, this is what this program doing. So let's see if I want to modify something. Let's assume that one of the students, and I want to do something else. So I'm going to stop this program now. Bye-bye. It's going to go. I don't know if I did mention that I include some menus. Yes, I did include the menus. When I create this thing, I create some menus. I think I forgot to mention that the API offer. Those are the menus that I'm using there. You could read this thing here. Those are basic menus for allowing you to stop, start, finish the program, or reset the program, or reset the playback session. Okay, good. You could read that and play with that. So suppose I want to say, I want to do something else. I show another platform. I'm going to create that artificially. And then I'm going to create then here, when I create the initialize, I'm going to put another object. I'm going to call this hypothetical car number 2. And I will show this in, suppose, blue. I could use RGB color if you want, okay? But I don't want to spend time showing this in RGB. Okay, that will be a handle to certain things which are going to be lined in blue. At the moment, it's showing nothing. But I may use here, in my animation, calling this helper function in the Or you could use this for doing your animation your way using the function set, which is in MATLAB, for changing properties of graphic. And I'm going to say that I'm going to create another thing here. And I'm going to say that this is the same pose that I had before. Yes, it's going to be equal to the first one. All right. And I'm going to make this x and y of this pose, the component 1 and 2. I'm going to do equal to 0 dot suppose half a meter and half a meter shift in x and y. I want to do that, and I'm going to show that here. So that could be interesting if you want to show the ground through, which is something that we are getting here, and what is proposed in your kinematic model. You could do that to compare this when you are running the thing. So let me see. And here we have, I create this sort of shade here, shadow. Yeah. I'm not showing this, I'm just showing this shape, not this, the position using any asterisk here. You could add that thing as well. Well, I create now my second platform. Yeah. Just playing a bit and modifying that program. So this is doing everything now, but of course you have to do a lot more. Yeah. But this could be, suppose, the ground through, and this could be your kinematic prediction, because you could be running the kinematic model at each event using information which you got from the dead reckoning sensor. You could do that. This is what you were doing in simulation before, in tutorial number 2, assuming certain sequence of input. But now the input are coming from the dataset. The dataset is telling you at this moment, when there is a dead reckoning event, it's telling you now at this moment, we are receiving data from the dead reckoning sensor, from the longitudinal velocity sensor, and from the angular, and from the heading rate sensor. And these are the values you need to use later for keeping, applying your kinematic model frequently enough for doing the proper prediction. All right. Of course, if I do reset here, in this case, going to come back to the initial position and restart the playback session. Yeah. Okay. Let me see, I'm missing anything? No, I think we saw all the capabilities of this program. So I expect you to reuse this. You could do whatever you want. You could cannibalize this program. You could use this structure and say, no, I don't like to be initializing these things. Suppose here, where are the things here? Let me see here. I want to create this inside of my function in which I create all the, all the feature which I want to show in the global coordinate frame. You put everything here. Some of the objects will be static. In this way, I was in the same figure showing the walls and the poles, which are static objects, so I don't need to be refreshing anything there. I just plot this object once. And there are other features which I want to show dynamically. For instance, the position of the ground through, or the hypothetical platform, showing position and orientation according to the ground through. And also another showing my prediction using the kinematic model. Or other dynamic object could be, I'm showing as well here, let me see, and the LiDAR points, but not in the LiDAR coordinate frame, but in the global one, according to the transformation, the proper one, from local to global, and these things. And you may show many other things there. So that is up to you, depending on what you want to solve in the project number 1. All right, I think I did mention everything. Yes. Yeah, I think everything is here. I think I will stop this recording now.